to the ND score. But the TA hour, the third TA hour from this week will become the preview of the next week course material. Yeah, because last week we did a vote. So most of wants a preview for the course material. But if you have any questions of solutions to the test, solutions about the test, you can come to office hour and STAs. Okay, so we start from the monotone convergence theorem, which we use in last problem. Because in last problem we need the fact that if an plus 1 is larger than an larger than an minus 1. Oh. We need that this sequence is converged. So we need to use monotone convergence theorem to prove that, to state that the limits of such sequence exist. Okay, so monotone convergence theorem says that every bounded and monotone sequence converges to its limits. If an is an increasing sequence, then it converges to its supplement. If an is decreasing, then it converges to its infinite. Okay, I will prove the supplement case. So suppose an is an increasing sequence. We know that an is none because an is bounded and non-empty. So by this upper bound property, its supplement exists. Let's call it A exists. Then we want to show that A is the limit of the sequence. Okay, so for every epsilon that is larger than 0, we must have, there exists n such that a minus an is smaller than epsilon. Oh yes. For all n is larger than n. Or otherwise, a minus epsilon will be a new upper bound of an. So a is not this upper bound, which is a contradiction. I think I write it down. Otherwise, a minus epsilon is upper bound of an. So using this property, we have a minus an is more than epsilon for every n larger than n, which implies limit a n is equal to n a. That's the proof of monotone convergence theorem. Oh, you need to prove the decreasing case, but it is symmetric because you use the you change the least upper bound property to the largest lower bound property and says in an is equal to a, something like that. Yes, you can do it as a practice. Any questions? Okay, if there's no question, I will go to complete space and completion theorem. Complete space and completion theorem. So we have shown in the test that, or in course that, converged sequence implies Cauchy. That is, every converged sequence is a Cauchy sequence. But how about the converse? Is Cauchy sequence implies that such sequence converges? Is this true? Can somebody tell me if this is true or false? False. False. Yes. Yes, this is false. Why? Because consider in rational numbers and the sequence 3, 3.1, 3.14, 3.141, 2 pi. This sequence is a Cauchy sequence in rational numbers but it does not converge in Q because pi is not in Q. So unfortunately, this is not two-way. But if we can define some space that Cauchy sequence will converges, then this will be equivalent. So we define complete space, a complete metric space. That's every Cauchy sequence converge in say in X, the metric space. So if a metric space X is such that every Cauchy sequence converge in X, we say this metric space is complete. So now, what kind of space, metric space, is complete? For example, compact space are complete. Why? Because compact space, if a space is compact, then it is sequentially compact, such that any infinite sequence, like it will contains a converged subsequence. So you can use this fact to prove that the Cauchy sequence will converge in a compact space. So when closed subset of compact space or complete space Why? Because if there's a Cauchy sequence in a closed subspace, then it is a Cauchy sequence in a complete subspace. So it converges in the large complete space. So because closed subsets must contain its limit point. So it must contain the limits. So closed subsets of complete space is complete. Q is not complete. Yeah, because we show it here. The Cauchy sequence here is not do not converge in Q, so it is not complete. But rational numbers or Rn is complete. Because every Cauchy sequence is bounded. You can bound the Cauchy sequence in a box or in a ball that is compact. So compact spaces are complete. So R is complete because the Cauchy sequence will converge in the compact space. And so we can see that we can somehow extend the metric space to a larger complete metric space from the example of Q rational numbers and real numbers. We can extend the rational numbers to real numbers, right? But how can we do this? The completion theory says that every metric space can be completed. So we can extend every metric space to a complete metric space. So we said if M can be completed to M hat if then M is a dense metric subspace of M hat. So the completion of Q is R because Q is a dense metric subspace of R. So the M hat contains all the limits of M. So M hat is that complete. Okay, I'll draw a graph. Suppose this is our metric space, a R2, such that we drop some points. These are holes that this point is gone. And then M is not complete because we can easily find some Cauchy sequence that converge toward this point. So this space is not complete. Yeah, also we can find some Cauchy sequence that converge toward this point. But after completion, this space will become R2. That refills the hole in metric space M. Okay, for examples, like the open interval 0, 1 can be completed to 0, 1 closed interval. So we fills the boundary, the disappear boundary. R is equal to 0 can be extended to R. And rationals can be extended to rationals. Although the whole of rational is more than rational itself.
So can you tell us why? So suppose I take out the unit circle.
Yes.
Then why that I cannot complete it?
Oh, this is not the unit circle. This is the point.
I know, but yeah, I mean, if you take only one point, then you can complete it. But suppose I take out a whole a unit circle, that you have a whole.
Yes.
So why isn't that completable?
You mean?
So R squared, but take out the unit circle. So
Unit circle.
you have a hole in the middle. Yeah.
This is a this is a complete space, because every Cauchy sequence in here will converge in space.
But then is it a? Oh, I see. So
if you take the closed unit circle, that the boundary becomes open, then this is not complete. But after completion,
I
it
see.
will
So
become the closed.
If I add the boundary.
Yes, you'll become complete. So this process is called completion.
I see. So how is that different from from going from open to closed?
Going from closed set
from a set to its closure.
Because a closed set is not necessarily a complete space. For example, the Q, if we choose our matrix space to be rationals, then it is itself closed and open, but it is not complete. Because the matrix space itself is closed. But we can somehow find a sequence that do not converge in Q. Because a closed set is a set that contains its own limit points. But those limit points must first exist in Q. So we cannot take the points like square root 2 in R to be the limit point in Q if the whole matrix space is Q, because we don't know what is square root 2. So the question is how to construct such complete space. If we have a matrix space, and how to construct the completion. Recall that when we are constructing real numbers from rational numbers, at that time we don't know what is a number called square root 2. There's square root 2. We can say we add square root 2 to the rational numbers, so it will become the real numbers. But we can observe square root 2 by the rationals that is smaller than square root 2. So we let the rational numbers that is smaller than rational 2, square root 2 to be the square root 2 itself. So that's the Dedekind cut. So in this metric space M, although we cannot build the hole directly by saying that we add P into the space M, but we can observe the point P by the Cauchy sequence that converges toward P. We can observe that here is a point P, but it disappeared. So we that the Cauchy sequence Pn that An that converges toward P maps to the point P. So this sequence is An, and this sequence Bn. And with that, the Cauchy sequence Bn that converges to Q maps to Q. That's how we define our new points in our completed space. Okay, so now we have points. What about the metric? How can we find the distance between two holes? Because we cannot measure it directly. However, we know that there must be two Cauchy sequences that converge toward these 2 points. And as n tends to infinity, the limit distance of An and Bn will be the distance of P and Q. So we can use these 2 Cauchy sequences to define the distance of the holes. So let's see in the collection of Cauchy sequence in M. And for any Cauchy sequence An and Bn, we define the distance of 2 Cauchy sequences to be the limit distance of the 2 sequences. So this will almost be the metric in our new space. But here's one problem. We know that in metric space, there's only one point that has 0 distance to a point x. That is point x itself. But if we map all Cauchy sequences that converge to P, then if there's another sequence Cn, then An and Cn has distance 0. So this map do not construct a complete space because it does not satisfy the metric condition. How can we deal with this problem? If we can say that we let all the Cauchy sequence that converge to the point P to be the point P itself, then we can fix this problem. So we say An is equivalent to Bn if D, An, and Bn equals 0. That is, An and Bn are both converge to P. if AN is equivalent with BN and BN is equivalent with CN, we know that AN is equivalent with CN. So you will have the equivalent class that all the Cauchy sequence in the class are equivalent. So the last step is that M hat to be the Cauchy sequence modulo the equivalence relation, such that all P equivalence Q are the same points. So if we define our M hat to be this, we need to check some conditions. So first that D is a well-defined metric. On M hat. So you need to check the three conditions of metric, such as symmetry or something. And the well-definedness is that because we use two Cauchy sequence to measure the distance between two holes, it must be consistent if we change to another two sequence, Cn and Dn. Because you cannot say if we change the sequence, the distance of P and Q will vary. So you need to check the well-definedness. So second, M is embedding in M hat, or M is a subset in N hat. Because for a point Y in M, there's a Cauchy sequence Y, 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 that tends to Y. So this sequence will be mapped to the point Y in our complete space. So M is a submetric space of M hat. That's third one. And third one is M hat is complete. Yeah, I will not go through the proof here. So if you are interested about the complete proof, you can see proof. Which is a really well written book.
We should like put on the page.
I'll put on page. I think is you just go to the subsection called completion. Yes. I forgot the page.
Let me find that.
That's why is such completion is unique. There's only one M hat such that it is the completion of M. That is the whole structure of completion theory.
Like uniqueness here is like somewhat subtle, like up to some kind of like metric space isomorphism.
Yes, this is a isometry embedding. Yes, but
I'm not so sure how to explain this here. Now you can see if we have constructed some extra structure on it, and we can rename it. However, through the rename, we will not change. Through the rename, we will not change anything, except the name. and that would be called isomorphic or isomorphism in math.
For the proof, it's page 119 to 121.
Okay, 119 to
121.
121.
That's where he proves the completion theorem.
Know that we cannot use D in directly in our completion space. We need to change it to a bigger D that is defined on the equivalent class. Because if we have to the well-definedness of the small metric D, then we can change the Cauchy sequence to be the whole equivalent class. Because it is no matter we pick AN, BN, or PN in this equivalent class, we can just pick one sequence to represent the whole equivalent class. So do we have time? Okay, I have seven minutes left. Oh, is there any questions?
Did Ruding mention this?
Do Ruding?
I can check it. I don't think so.
Yes, I don't remember.
You know what? Yes, in exercise 24.
Oh,
And it's a long exercise. It has A, B, C, D, E to do. So
okay. So the last thing I want to talk about is the limit soup. The limit soup of a sequence AN is the soup of the subsequent limits of AN. Or there's another definition such that it is the limit soup. Okay, this might be hard to read, so I will give an example. So, for example, 1 minus 1 over 2 minus 1 is 3 minus 1. So what is the limit soup of this sequence? We can easily see that this sequence limit does not exist because you will tend to 0 and minus 1. But if we can choose a subsequence from this sequence to make the limits to be the biggest, then that will be the limit soup. So we can choose 1 over 2, 1 over 3, then this will to a 0. So say Bn. So limit soup of Bn is 0. Okay, so we can similarly define the limit in, that is the implement of subsequent limits of An. So in this case, limit in of Bn is -1. Because we can choose all the -1 from the sequence. Okay, some properties of limit soup. Is limit soup An plus limit soup Bn equals limit soup An plus Bn? Is this true? So this, unfortunately, is not true, because we can find a sequence 1, -1, 1, -1, and the sequence -1, 1, -1, 1. So in this case, the limit soup of this sequence equals 1. And this case, limit soup equals 1 as well. But if we add them together, it will become 0, 0, 0. So limit soup equals 0. So this is not whole general loop. So second one is limit soup An equals limit soup CAN. C is a constant that not equal to 0.
Larger or 0, not equal to 0.
Oh, is oh, it's always Okay, so this is not true as well, because you can multiply this C equals -1. So,
Oh, sorry. I thought I asked the wrong question.
so in this case, the limit soup is still 1, but C times limit soup is not limit soup CAN. So this is not true, and this is not true. So last property limits An exists if and only if limits soup An equals limits in An. Okay, I see time's up, so I will stop it here. Any questions?
So why this kind of like limit soup and limit in thing is important is because like we're thinking about something like limits. We're thinking about like to control it by 2 ways. Right. But when we're thinking about like limit soup and limit inf, if you can do that separately, in some case like deal with 2 sides simultaneously is hard, but one side is not that hard. So you just like, okay, limit soup equals to this one, limit inf equals to this one. So limit soup equals limit inf and